back in. We're doing the Riddler Classic now, so I'll restart the timer, and then we can give it a go. All right. So the Riddler Classics are usually a lot harder, and the only thing I've gotten spoiled about this is that it's about ice, and I don't know what that means. All right, sick. Let's start it. All right. Winter is almost upon us, at least for those of us in the Northern Hemisphere. Fun fact, like 80% of humans live in the Northern Hemisphere. Official Ice Master and Deliverer Kristoff and his trusty pal Sven are preparing ice cubes that will be sent to the hot springs where Kristoff's extended family lives. At the moment, they are studying a cube whose side lengths measure 1 meter, meaning its surface area to volume ratio is 6. Kristoff doesn't particularly care about units here, but they are in inverse meters. Sven is concerned that much ice will melt before they reach the hot springs, so he suggests to Kristoff that they cut along a single plane to minimize the surface area to volume ratio of the larger resulting piece. Along which plane should Kristoff cut the ice, and what will the resulting surface area to volume ratio be? Oh shit. Okay. So this is a tricky one. Okay. So as always, we'll start by drawing it out, and then we'll see where we get from there. Okay. All right. And so this is 1 meter. This is 1 meter. And which one did I do? This is 1 meter. Okay. And so the volume is, the volume is the volume. In this case, it's 1 meter cubed. And then the surface area for this particular one is this side times 2 plus this side times 2 plus this side times 2. And so that is how they got the 6, is that each of those is 2. So it's length times width times 2 plus length times height times 2 plus width times height times 2. And that equals 1 times 2 plus 1 times 2 plus 1 times 2. And so 6 meters. And then the surface area to volume ratio is 6, right? Yeah, perfect. Because it's 6 meters divided by 1 meter cubed. And that equals whatever, 6. Oh, this should be meters squared. Whoa. All right. And this is meters to the -1. All right. We got a chat message. I got my first chat message. So let's make sure we really stop down and read this. All right. This is Stuart from Twitter. Haven't solved this week's yet. Looking forward to solving vicariously through you today. Oh God, that's nerve-wracking. Thanks, bud. Yeah, we're working through it. I'm not excited about this one. This is a pain. Because surface areas are annoying to calculate is the reasoning why, right? Volumes are also annoying to calculate. Depending on how we cut this cube, you're going to get a bunch of triangles. And then you're going to have to do this math kind of for all of your triangles. They can even be that other shape where it's a rectangle and a triangle. Like this this shape. And so you have to kind of componentize it as a result. There's also going to be a bunch of angles. So finding the optimal way to do this is going to be weird. And I'm looking ahead. Basically, I don't know of an easy way to do this. So we use a single plane to minimize the surface area to volume ratio. Okay. So minimizing the surface area to volume ratio means that we want the surface area to be small, but the volume to be large. Now, if we just like think in the abstract, what are the best ways to do that? It means, so let's just write that out because that's something we're going to come back to. Surface area should be small. And volume should be relatively, but it should be big, right? And so because it's a ratio, obviously these things are relative. And because we're using a single plane cut, we can expect no curvature or anything like that. It's just going to be straight lines all around. And so let's go through a couple of examples, right? Like I'm thinking that we look at the extremes, we see what those look like, and then we go on from there. The one thing I'm debating doing, just because it's kind of fun, is opening up SolidWorks, which I'll do. All right, so we can tick off that we've read the problem. Now we're into the solving part. And so why am I using SolidWorks? I don't know. It's kind of fun. It's going to cheat a little bit in the sense that it will do the surface area calculations and volume calculations for us, which means that all we'll have to do is define our cuts. But maybe we just use this for understanding the problem and not as much for solving it. Maybe this could, I'll tell you what my plan was a moment ago. My plan is to do some kind of just like basic cuts, right? What if we cut along this side? What if we cut along this side? It's the ratio of all the resulting pieces. Oh, shoot. So they want the whole meter of ice, meter cubed of ice. They don't want just the piece of it. If that's the case, that is interesting. Of the larger resulting piece. It can't be larger. You can't cut things and make them larger. Sven is only concerned, all right. They cut the ice along a single plane of the larger resulting piece. So I think you cut it and then you're only taking the larger resulting piece. Stuart, what are we thinking about that? So just the larger resulting piece, so throw away the smaller resulting piece. That's what I think. And if they're equal, you throw away either one. So let's make this diagram, but cooler. Which is, here's our block of ice. Get it? It's cooler. Make the smaller area have all the surface area, perhaps. That's really smart. Okay. So what we can do, cool. How do we make, is there a finite amount of surface area though? I don't think that this is a zero-sum game. I think that you can make a cut so that there's a lot of surface area. For example, I'll kind of demo this. This will be fun. This is my ice block. So if we have one that includes all the corners, I think that would have a lot more surface area than if you just did a sheer cut like a guillotine, through the side. I think that the total surface area, if you did a cut along a plane right here, would be the resulting would almost be 6, depending on where you make that cut. And then the volume would go down appropriately. And so let's just let's just do a cut, and I'll show y'all what I mean. Nice. Okay, so that's a cut that we could make. And so if we did this, we reduced the volume by a little bit, and we actually reduced the surface area probably by a little bit. My guess is that this new figure will have less surface area. Mass properties is actually the way you do it. So the volume now is 0.83, and the surface area is 5.37. I'm in inches, but just ignore that. Pretend like we're in meters. And so I made this cut, and we decreased the volume, we decreased the surface area, and now let's look at the resulting ratio of those two. It was 5.37 and 0.83. And so the ratio of this to this is 6.4. So we did a bad job. We took our cube and we cut the surface area, we cut the volume, and now it's a bigger number than 6. And so let's think about why, looking at this here. The reason is, okay, let's think this out. What are the best things in general, surface area to volume wise? I think it's a sphere. I'm fairly confident that a sphere has the best surface area to volume ratio. Surface area is small, volume is big. The reason we don't use those for things like cans of soda is because they don't stack well. And so we want our thing to be the most sphere-like. I think that's right. And so this cut that we made makes it look more like a sphere maybe to me. But I don't actually think that it helps. So we can go through, let's just like sanity check ourselves here. I'm gonna sanity check myself because I need that. So we'll reference off this plane, but we'll go in like 0.2, right? And so flip. And so this is the result of doing what I called, yeah, I guarantee you watch the same YouTube video about the miraculous invention of the aluminum beverage can. It's a top 10 video on YouTube. All right, so we're gonna move this in, and this is what I'm calling the guillotine method, where you're just kind of chopping it this way. This is absolutely gonna make it worse because we're reducing the volume. God, I really hope this makes it worse, because in my mind, the thing that would be the worst case for this at all is a flat plate. Like a really flat plate has minimal volume and a ton of surface area. It doesn't have to be a plate, but like a flat plane, something very thin. And so what we're doing here is we're making it more like a plate. We're cutting it like this. And so I'm pretty sure that this is going to be worse. And so let's make sure. Let's make sure. Our volume is 0.8. Our surface area is 5.2. And so this is now 5.2 and this is 0.8. And it's 6.5. Great. It's worse. All right. So that's good. Again, we're not going to solve the problem maybe using SolidWorks. I think we can be a little bit better, but I also think that this is a good way just to kind of check ourselves quickly. All right, so we've tried what I'm calling the guillotine method of cutting, making a plate. That made it worse. We tried cutting in a way that involved 3 of the corners. That made it worse. So far I haven't found a way to decrease it from 6. We're hard stuck at 6. And so let's use the principles that we were talking about and try and make it better here. We got to redo this. All right, so this was one of the cuts that we made, and this resulted in it being 4.6. The other cut that we made was an offset inwards. And so what else can we do? Well, let's try cutting a tiny corner off. Let's try just doing, this was a big corner that we cut off. This is the biggest corner that you could cut off almost. Let's try doing, and so my thought is that this will finally get us below 6. Because we are making it more cube-like. Okay, cool. We just took off a little corner. This has to work. We're making it more cube-like, and the ratio would be better. If you guys think otherwise, I don't know. Now would be your time to doubt. But okay, maybe this is our sign that we should switch away from using SolidWorks, because it's annoying me, A, and then B, I don't know if it's the right thing to do, because we're going to want to be able to more quickly change the variables that we're dealing with, right? And so if we want to find the volume of the piece that we cut off, it's a triangle, and it's going to have these 3 sides to it. I think in every case our cut is going to, I don't know if this is true. I want to shave off a corner, but I don't know if that will guarantee us the best case. The alternatives would be shaving off a whole piece like that. It's shaving off 2 corners, I guess, would be the way that I would say that. And so we can shave off 1 corner, 2 corners. We can also shave off 3 corners, but barely, because if you include 1, 2, 3 corners, you're getting dangerously close to having half of it included. I don't know. Cutting off 3 corners is weird. What if that's the move? You do some cut that goes here, and then parts of this. That sounds right to me, actually. Or that for some reason feels right to me. Because we only get 1 cut, and I'm worried that we're going to start taking off a lot of volume. Yeah. All right, well, let's do, I kind of want to stay in SolidWorks land because it makes my life easier. At least until corners do feel bad to have the, okay, yes. You're putting what I was thinking into a smart sounding thought, because corners are the flat plates of our situation. That doesn't make any sense. But the reason that spheres are great is that they don't have corners. And so cutting off the maximum number of corners seems like a good thing. That being said, when you cut off corners, you introduce new corners. And so that's bad too. I'm sounding so dumb, but I think that we're honing in on this, right? Okay, so let me draw what I kind of think I'm saying, and then we'll see where that gets us, right? If we cut off this section, it cuts off 2 corners. So how do I'll do a little snipping. I'll do a little snipping here. So if I cut off from here, this plane, right, then you're going to help. It's going to increase it, right? And now my theory is that cutting off that corner is strictly better than cutting off just one corner the same amount. And so I'm using this, but like I think that cutting off this in blue is better than cutting off this in red, which would be representative of cutting off just one corner. Because you're doing the same method twice. You're how do I word this? Yeah, you're cutting off two corners worth of inefficiencies as opposed to one. And so let's prove this real quick. If we can prove that, then let's try and take away three corners or something. I don't know. Let's extend it from there. But yeah, I don't know. This isn't going to be quick. We're already 28 minutes in. So all right. So I'm going to draw this triangle here, and we're going to make it a isosceles triangle 0.25. In my case, it's inches. In the problem's case, it's meters. So I hope that doesn't confuse too many people here. I'm also gonna do the same triangle here, and this is a representation of the cutting off one corner method. And so it's another isosceles. Gosh darn it, I did the same thing. This will be another isosceles triangle on the other plane that that represents us cutting off one corner. So now I gotta do that work. So let me shut up. And so now if I select this, I should be able to. I hate you. Gosh darn it. Oh, we're fighting a little bit with the software here because the volume isn't going down, even though I feel like I cut some things off of it. All right. Well, shoot. This is... All right, here we go. Oh my God. Last few thoughts before I have to log off. Intuition will get you halfway there. This becomes a minimizing loss problem. Writing out some loss functions that describe the ratio of the larger piece. Yes, this is where I was going to go, but I didn't want to. The ratio of the larger piece and finding the minimum derivative. Interesting. Finds like the only way to make this rigorous, but not sure how to get to that part yet. No worries, dude. This is super fun. I'm glad you were able to join. This makes the concept of streaming it pretty sweet. And so I totally agree with you on that part. What I want to avoid doing is having to make loss functions for 7 different configurations, if you will, like for the 1 corner, 2 corner, for all these different types of cuts that you could make. It might be inevitable, but yeah, that is. I think we're on the same wavelength. I think that it would be exactly right, because each of these is just going to be annoying geometry, if you will, where, all right, if we cut off this type of a cut, then here are all of our variables, and here are all of the angles that were that define that cut, and then minimizing for that. And so I think that's where this problem is headed. And I think we just jam it. So we can either debug SolidWorks or we could do the math. And I don't think debugging SolidWorks is a valid use, but no, I appreciate you stopping in. This is super fun. First time chatter too. That's cool. Makes sense. I'm a first time streamer. Okay. So, sweet. Let's open up some sort of way to get our geometry right. So let's talk about getting this into a math problem. Probably the easiest way to do it is to know that our surface area starts at 6 and then has some removed and some added. The amount that's both removed and added is going to be equal to or related to the cut, which is a smaller triangle, which is just going to be a little bit easier to deal with. And so let's start from there. So if we just look at the new triangle that we're cutting, I'm gonna go with the single corner cut to start. I kind of think I might regret that, but we're gonna do that. It's going to be it's not gonna necessarily be a right angle. Yes, it will be a right angle because it includes a corner. Cool. So it's gonna have angle A, angle B, and then it will also have an angle C. So this would be like A and C, and then there'll be a third triangle. This is not probably the best way to organize it, but whatever. That will be C and B. I might have lied. There are 4 triangles. And so the fourth one is not necessarily a right triangle because it is ABC. And so this one's just ABC like this. And so this one right here, by the way, okay, this is good. So let's give these triangles names as we are known to do. This will be triangle 1, triangle 2, triangle 3, triangle 4. When we're finding our ending surface area after a 1 corner cut, it will be 6 minus, because we're actually removing these ones, so the surface area of corner 1 or of triangle 1 minus SA2 minus SA3 plus SA4, because SA4 is the triangle that we're adding. Now, the volume, this is SA star. Volume star is equal to 1 minus the volume of triangle ABC. Okay. And so now what we do is we find these surface area calculations, basically put this all in terms of oh no, I messed up, guys. Is that all we have to figure out? I think there might be one more variable here, because the angle of the cuts matters, but also the scale, right? Like you could have that cut, but you could also, I'll use a different color, have this cut. And it could be the same darn triangle, but with bigger side lengths. You know what I mean? And if that is the case, then that introduces another variable into this. So it's the angle and the side length of just like one of these, and that'll pepper through the rest of it, I think. Okay, so the cool part is these things will be related. It's just that it's gonna be so frustrating. So for example, this line right here, not that line, this line right here is gonna be the same as like this line right here, I think. And then this line right here is going to be the same as this line right here. Basically, if you look at this one, you can see that there are only three lines, three edges, and here it looks like there are many more. It's because they're all being represented several different times. And so the actual number of things that we have to represent is smaller. And so we will be dealing with that. Okay. So it's probably time for me to buckle into it and shut up and solve stuff. But also cool that people are here. Like I decided to do this on for a couple of reasons. One being I've got time now in a bit of a work break, and so I've got time to set things up and think about things like this. And the other one is that I'm kind of doing this regardless, right? Like I would be doing this on a Saturday morning, and so I wanted to do this in a way that other people couldn't be involved as much as they wanted to, and so. We had Stuart in the chat earlier. That was really fun, and they gave some pretty sweet advice, and so I appreciate it. Spoilers, don't give me those, but advice and I've never solved this problem. I've never looked at this problem before we started 47 minutes ago. So yeah, I guess I'm all ears. All right. So that being said, long diatribe over. Let's do this. So let's start with this one. We've already drawn it out. The other thing that I'm realizing is I'm making it seem like there are a lot of variables in here. We can drastically narrow that down to 3. And then we can just iterate on those. Oh my God, this is looking a lot easier now that I'm thinking about it. So let me say what I mean, right? I'll take a little snip of this and I'll show you. But this problem just got easier. This is a variable, how long this side length is. This is a variable, how long this side length is. And then, come on, you guys know what the next one is. This is a variable. So there's only 3 variables for the corner cut. Now, we know that they are bounded, right? They're bounded to be between 0 and 1. And then we come up with the equations for these, not based on the angle, but based on the side length. That's super easy to do. And then using Python, we just brute force it and find a minimum. That sounds easy. You know what I mean? So let's do it. Surface area 1. Okay, so let's draw the third colored line in here, and then let's get to town. This is fun. We're cooking with gas, everybody. Okay, those are our 3 side lengths. Sick. All right, I'm skipping ahead a little bit. Let's not. Let's just do this. All right, SA1 is equal to L blue times L green times 1/2. And then this will extend for SA2 equals L green times L purple times 1/2. SA3 equals L blue times L purple times 1/2. Cool. SA4 is spicy. And there's absolutely an easy method that we can just kind of cheat to get there. Surface or area triangle, 3 side lengths. Okay, well that's almost easy. We'll just keep this over here and copy that down. Square root P minus A, P minus B, P minus C. Okay, sure. We're totally like changing the units for this, but basically we're gonna program this in probably Python, and then once we do that, we're just gonna input these formulas and then generate the variables and have it spit out the values. So we're not actually gonna do the calculations that the computer will be for these, and so we can translate our equations when we're actually inputting it over there. So this is Heron's formula. Okay, sick. And then the volume. That's the last piece that we need to define. And so volume of triangle A, B, C, or prism, or whatever you'd call it. Tetrahedron. God damn it. Oh yeah. This is where I was so close. Hey Zach, how are you doing? This is fun because I used to get really nervous about like solving problems in front of a class or whatever. And this is now just what I'm choosing to do. So people can yell out answers and that's fine. Hey man, this is fun. This problem is really cool. And so face area, no, I want volume. Yes, look at that. Yeah, this problem so far has been good. There's gonna be a couple different configurations, and then we're gonna brute force our way through some of those. Not brute force, but find the minimum. And so yeah, I've been having fun with it. It doesn't make sense from like a theoretical point of view because they want a lot of ice, and so I have issues with the premise. Like, why not just bring all the ice, let some of it melt? Admittedly, probably more than if it was a sphere, but the fact that you're starting with more means you probably have more to give. So there's logical fallacies there, but we're gonna ignore that. Don't you? Okay, wait. Do I remember this right? Don't you just do the volume of the bottom one, or the surface area of the bottom one times the height divided by, okay, here we go. The volume of a regular, I don't want that. Oh my God. Yeah, no, you do that. 100%. Because it's a section of a cube. So you basically do the cube formula and divide it by 2. Oh my God, that's so much easier than I was letting on. Let me double down, but let's see if this works. You go this times this times this, which would get you the area of this cube, but you don't have this cube, do you? You have half of it, and so that's why you divide it by 2. This diagram doesn't help at all, but I'm pretty sure that's right. Okay, so let's give that a whirl. It's equal to LPLG brother bear. I'm not sure, but let's no, that's right. It's right. Okay, so let's do this. Let me tell you, if you thought divide by 6 instead of 2, then that is something I agree with. But so I like where you're at. Okay, we'll amend that in our little thing here. Divide by 6, and we're dividing it by 6 because you have to divide up. There are three portions at which you're cutting it by 2, for the 3 sides of the 3 upper edges of the tetrahedron, if you will. Okay, so I can rationalize that, and to be honest, I trust you. So let's just go from there. All right. People later we're discussing where this 1/6 comes from. 1/3 is from the formula. 1/2 from the area of the base. So the area of the base, meaning you had to do this L1 times L2 divided by this L1 times L2 divided by 2. The other third comes from the fact that you're extending it into the third dimension. Exactly. 1/3 area times base height. That's right. Cool. And so we're showing it here as 1/6, but that's a bit of a clarification, honestly, for me, on where that 1/6 is coming from. Okay. So let's code in front of people. Holy crap. So I can see this because I'm basically going to be putting all these in Python now. And so SA, oh gosh, from length. We don't love how this is labeled, but this is a good program. Okay, this is good practice for me. So def surface area from length, and give me L1 and give me L2, and I will just return L1 times L2 divided by 2. This is for right angles. There's also sometimes you give me L3. And so if there's no L3, then just do this. So this is the case in which it's a right angle. If it's a right angle, I'm just going to give you the L1 and L2. Otherwise, case in which it's not a right triangle. This is where we have to use Heron's formula. And that looks like this. So we have to define P, which is equal to, oh God, All right, we're back. So, where we're at, just for everyone, is that we've got our formulas for how to, for what cuts look like. And so we're going to do a single corner cut. It will look like this when we're done. And we're going to explore what the various cut configurations will do to our surface area to volume ratio. And so we just parameterized it, and so turned it into some sort of an equation that will give us the surface area and volume of our shapes. Now we're going to iterate through various lengths of cuts that we can do. And so this one had all three side lengths being the same length. Let's try that for various lengths. So we're going to do that. We're going to see what the best case one corner cut looks like. And then we're going to see where that leaves us. There are other types of cuts that can be done, and we're going to deal with that. We're going to deal with that later. So and at this point, if ratio star is less than our ratio, then we print, hey, found a new one, and make our ratio equal to ratio star, and then along with this, we can print use length following lengths. All right, so this will be our little printout. It'll spam a bunch of stuff at the beginning because it'll be finding minimums quickly, and then it should settle out as it finds the best one. there are better ways to do this than printing to the console, but that's not why you came here. You came here to see it be speed run in less than 2 hours. So that's what we're gonna do. All right. So I think we're ready to run this, and then I can actually say new ratio, and then tell me the ratios. Cool. Hey, everyone's happy. All right. L3, yeah. Okay. I tried to get a little cute with it. It doesn't like that. Can I do this? No. Oh my god, I'm in JavaScript again. None. I think I can do that. Cool. Typo. I got a complex number. Holy crap. Oh, brother bear. The ratio between my surface area and volume is complex, which means it's pretty royally fucked. It's just a quadratic formula. The lengths of that triangle isn't L1, L2. It's the hypotenuses. Holy crap. That's the smartest thing I've ever heard. John is Larry's going off. Zach is actually helping. Wow, that is so right. That's so cool. It's only for the case in this third triangle, but that's a really good point. Okay, cool. So, yeah, none of you guys helped. Bro, I'm helping, bro. No, Zach helped. Zach gets credit. L. So now, John is Larry. You can help me by telling me what the formula for for this is. Plus L2 squared square root. And we do this 3 times. Okay, so we now use L2 and L3 and then L3 and L1, and that gives us A, B, and C. And then these use A, B, and C now. Mad triangles. Is this triangles or what? Yeah, we're in triangle world. I really do hope that the answer to this portion is the actual. Well, we're gonna have to try the other configurations. L1, L2, L2, L3. Okay. Okay. Oh my God, look at this. We're minimizing it. We got it down to 5.995. Oh, that's so weird. So it really likes it when one of the side lengths is very long. And this is actually confirming what we were thinking earlier. So while this is running, I'll draw another cut. And this is going to be fun. This is actually a lot. This is exciting. Everybody buckle in. We're having fun now. All right. So what we did right here, right, is we iterated through a bunch of different cuts. And what it seems like the computer is preferring is cuts that have one really long side length. And what's interesting about that is kind of indicative of it wanting the cut to go all the way through one of the sides. Because we limited it to cutting away one corner, it can't include 2 corners. And so I think what it's prodding us towards is at least a 2-corner cut solution. Scared of this new shape on the screen. Yeah, I'm showing a different configuration for a cut. It cuts the other way and it cuts like that, right? And so this is a 2-corner cut that we're looking at here. I'm gonna play some Melee. Hell yeah, dude. Yeah, let's play Melee later. So this is a 2-corner cut, and what we just saw by doing this one here is that it was preferring one of the side lengths. We can actually check on it. Yeah, one of the side lengths to be really, really, really big. And so when one of the side lengths is really big, it's almost like it wants it to be a 2-corner cut. And so I'll show you what I mean. If this is 0.99, this is what our current thing is liking. It's saying that this is the best one. Instead of if this is the best kind of cut we can do with a 1-corner cut, then I bet you we can get even better numbers using a 2-corner cut. Now, if we were to extrapolate, what about a 3-corner cut? You're probably right, is the unfortunate answer. Yeah, a 3-corner cut is probably going to be better, and then we'll have to do it a third time. And so now I'm just reducing the resolution to see what it likes. Oh, that's interesting. It likes 0.26, 0.26, 0.99. That is a little surprising. That's almost exactly what I have drawn here. Cool. So this is how about a 6-corner cut? That is the equivalent to just missing. Wait, is that right? There's 8 corners total. Wait, A 6 corner cut is what you get if you leave. I don't know, whatever it is. You guys know. I meant an 8 corner cut. Okay. I did the rest of the joke for you. Yeah, man, we can do an 8 corner cut. That's so interesting that this is what it prefers, because it I guess why it stays at 0.26, 0.26, 0.99 is a little interesting to me. I would have assumed that these 0.26s would have been 0.25s or something, or 1/3, or something that's geometrically kind of stable. 0.26 is just a little curious. The funny part too is that the new ratio isn't that different. It's 5.96. So we're gonna push on, right? So we got it down to 5.96, which is an improvement, and we know how we got there. We can increase the resolution and get there, find the absolute minimum here. But at that point, we're talking down at the 10,000th level of the ratio. And so what I think we do is we take our learnings from this 1 corner cut, extend it to this 2 corner cut, and see what happens from there. But again, this is my first time doing this in a year. So people, if you have feedback, I've got 4 viewers, which is actually a little crazy. Let me know. I do kind of plan on doing this more often. And I'm having fun already. So we got another first time chatter who's talking about how legit my copy of SolidWorks is. I couldn't agree more. All right, so let's start programming away for the 2 corner cut configuration. It's going to be a lot easier, I think. So let's go to this, right? What we're taking away is 4 shapes, 2 of which are right angles. We'll just put a little _2. Ooh, not there. Because we're taking away surface area from this little right triangle, this little right triangle, and then the rectangles that those side lengths defined. And so this is L1, this is L2, and then we have this rectangle that has L2 as its height and 1 as its length, and then this one which has L1 and 1. And so again, we'll write out our equations like we did here for the surface area star, volume star, and how we get those. Okay, so SA star is equal to 6 minus oh gosh, what am I doing here? I gotta label these. This is SA1, SA2, all these essays. What is this, English class? 2 times SA1 minus SA2 minus SA3. I'm forgetting a part. I keep toggling between stuff. I need to get better at that. Sorry. This part gets added, and so we have to add that to our surface area. And so we define this by the hypotenuse, and then side length of 1. And so it's again it's just a rectangle. This part here is 1, and then this part here is L3. And so, and then this is going to be SA4. Okay, cool. So we add SA4. Nice. Volume star is equal to 1 minus the area of this triangle times 1. So volume of I can just write out the math for it. People will understand. It's L1 times L2 times 1/2 times the length, which is 1. And that represents the new volume. The last part that we just got to write out just for Sandy's purposes and make sure everyone's on board here is what SA1, 2, and 3, and 4 are defined as. I'll probably block through these, but here we go. So SA1 is like I said, it's L1 times L2 times 1/2 because it's a right triangle. SA3 is equal to, I skipped to 3. Oops. It's equal to L1 times 1. And so, not going to bore you with writing out these other ones because they're very much the same. But now we're going to do the same exercise of iterating through and finding what the best lengths for L1 and L2 are for this two corner cut solution. So we're cutting off 2 corners and we're varying these 2 side lengths. What's interesting about this one compared to the last one is that we only have 2 variables, which makes it a little bit easier. I don't know. This is the 1 corner cut solution, and we're just going to comment all this out because we're done with you for now. Oh my god. Wait, isn't it Control K? Oh. It's not Control K. All right. But we are going to copy some of this because we're basically doing the same thing. So, whatever. Okay. Again, in the preceding little YouTube video, this will all be done in rapid pace, so people don't have to spend an hour and 40 minutes trying to solve this problem. So I apologize to all the live viewers, but it's kind of fun. I'm having fun. I hope you guys are too. Yeah, that's all I got. So I'm going to bring this over so I can see it. know what you guys are thinking. What's L3? Okay, so now we have the surface areas. And now the volume. And the volume is equal to V. Oh my god, what did I call it before? VABC. Okay, cool. Technically times 1. We'll just do that. Okay, sick. So now the rest of the logic should be the same of this. Minus SA2, minus SA3. We're actually doing 2 times this. It's a little bit different. And then the volume gets subtracted from AB. And again, it'll tell us the new ratio. Nobody told me I misspelled that. Okay, cool. So let's run it up. .15. If they're both 0.15, you get down to 5.95. And I think that's a new low score. We've got a new low score alert, 5.95. So let's write this down, because I don't think I did before when it was for the 1 corner cut. 5.956. 7. And that's using L1 of 0.15 and L2 of 0.15. So to show you over here in this extremely legal version of SolidWorks, these are both 0.15. Oh, I just typed in the same number. All right. And so if we make these both 0.15, that gave us the best surface area to volume ratio, assuming that this cut wasn't there. And so that's the best 2-cut solution, 2-corner cut solution. The unfortunate part is now we got to do 3 corners. Gosh darn it. Whoa. All right, you guys think what I'm thinking? Probably not, but hear me out, right? What we're doing here is we're going through and we're finding various low scores, right? Another way that we could do this is, because planes are defined by 3 points, we could just pick 3 arbitrary points on. Your intuition here is basically like kinda. So Namwobble is saying that my intuition of 5.95 being too high to be the right answer is kind of it. It's also that we don't know that it's the right answer, right? We know that we did a 1 corner cut method. We found a number that was very high. We did a 2 corner cut method. We found one that was lower. Why would we stop there? We have to push on further. And so, yeah. Now I'm trying to think if there's a way we can make it even more abstract. I don't think that's going to be within our realm. So let's add more corners. Oh man, I wish that there was what would have been a cool way to do this, and what I bet somebody else will be doing this who doesn't have a timer in front of them, is find a way to calculate the surface area and volume of a shape just given vertices. And then you could just pick planes and cut them that way. It's more open-ended, and so maybe it's a worse way to do it, but it's an interesting solution that I'm sure one of the great 538 people will do. Jiki Ko is saying that's like a cube, but not really. Yes. Yeah, so the problem is we start with a cube, like way up here, and this is our block of ice. And this block of ice has a ratio of surface area to volume of 6. And our goal through the problem is to make one cut, and using that one cut, get our ratio of surface area to volume as low as possible. We only take the piece the larger of the two pieces. So in this case, we cut off a corner, and the computer helped us find that this was the best way to cut off one corner. If you do this, then it goes to 5.9, I don't know, something, 5.98 maybe, which is lower than 6. Then if you did this instead of this, it goes down to 5.957 as your surface area to volume ratio. Now, what I'm wondering here is what's another configuration that we can do? And so let's try the 3-corner one, I guess. I don't really know how you cut off 3 corners. But that's why we have these things. Okay. So for this one, I'm actually going to, this will help a hurt. So I guess I'll show you what I mean, because in that case, it would definitely make it worse. In this case, I think that it may make it better. And so this kind of looks more like more of a sphere. It really doesn't. What I'm suggesting we do is we allow for cuts. Let me get a good angle like this, right? So we're allowing for cuts like this. Now, this is bad because what this in essence is a cut along this length and then a cut along the other end. And so if I draw this out, it's got cut 1, or what is functionally cut 1 right here, and then cut 2, which is this one. Now if we're to break what this is down, this is what I'm calling a guillotine cut right here, which does nothing but hurt your surface area to volume ratio, followed by either a 1-corner cut or a 2-corner cut, of which we've already minimized. So any time that you get more than 2 corners in the mix, I think it's just a compound cut of taking all of some off and then doing either a 1-corner or a 2-corner cut. Tell me I'm wrong. I would love. Tell me I'm wrong. Tell me I'm being lazy. Like, having other people hop on. I don't know. I've got a lot of ideas, and so I'm happy with the first effort, but I think we can do better. All right, so I'm going to show this part because it's kind of fun. Here's our answer. Here's our work. I think we submit it, and then I think we move on. But fun time. I appreciate all the homies coming through. Zach, good problem. Stuart, I appreciate your help. Jeff, that was truly helpful. John is Larry. That was equally helpful and true and infuriating. So whatever. I don't know. Appreciate it, everyone. We'll stop the timer because that'll be the last part. Sick. Bye, everybody.